In this video we're going to look at the mechanisms of organic chemistry required for AS chemistry exams, and in particular we're going to look at the nucleophilic substitution reactions of halogenoalkanes. Okay, so just a reminder that a nucleophile is an electron pair donor, and it is a substitution reaction because we're replacing an atom or a group of atoms by another atom or group of atoms. Okay. The electron pair on a nucleophile is attracted to an electron deficient carbon, which we show with our delta positive, and the nucleophile takes the place of a halogen atom. Therefore, it's a nucleophilic substitution reaction. Okay. So the first one of these we're going to look at is hydrolysis of halogenoalkanes to form alcohols. Now, if you're asked for the name of the mechanism is a nucleophilic substitution. It is just sometimes referred to as a hydrolysis because you can get this reaction to occur by just mixing a molecule with water. It occurs much more quickly if you use aqueous sodium hydroxide to produce your alcohol. And here we can see that using 1 bromopropane plus sodium hydroxide will give us alcohol plus sodium bromide as our unwanted side products. Again, I've got to reiterate, it is aqueous sodium hydroxide. That's very, very important for the outcome of the reaction. The mechanism shown here says we've got a lone pair of electrons on a oxygen atom of a hydroxide. We've got a negative charge, and we got a curly arrow attacking this electron deficient carbon. Carbon can only have 4 bonds at any one time, so it breaks the carbon-bromine bond simultaneously. Bromine takes one of carbon's electrons, so bromine becomes a bromide, and the carbon gains another electron from the oxygen to make our propan 1-ol. Remember, curly arrows only ever start from either a lone pair of electrons or a covalent bond, and a curly arrow represents the movement of a pair of electrons. The next reaction, I'll just move down, is the reaction of ammonia to form aminoalkanes, or the correct term is amines. So here the overall reaction would be 1 chloropropane reacting with 2 molecules of ammonia to form 1 molecule of propylamine plus 1 lot of ammonium chloride. Okay, the mechanism is shown here. Ammonia first of all acts as a nucleophile. The lone pair of electrons on the nitrogen attacks the electron deficient carbon. The carbon-chlorine bond breaks simultaneously, and then we're left with this intermediate here, where nitrogen now has got 4 bonds because it brought 3 hydrogens with it, and because it's used a pair of electrons to form this bond to carbon, one of these bonds now is a coordinate bond. So nitrogen is deficient in 1 electron. The nitrogen regains its electron by another molecule of ammonia coming along, acting as a base by removing a proton, and the bonding pair of electrons become nitrogen's lone pair. So you're left with an ammonium ion. Now, you don't have to show this bottom molecule of ammonia and this curly arrow to get the mark in the exam. One of the downsides to this reaction, though, is that the nitrogen still has a lone pair of electrons, so therefore it can still act as a nucleophile and react with another molecule of chloropropane. The reaction of cyanide to form nitriles, very useful reaction, because what this does, it extends the carbon chain. So we take 1 iodopropane, react with potassium cyanide, and we make butane not buta, butane, nitrile as our product. Potassium iodide is our side product. Again, the mechanism is similar. Lone pair on our nucleophile. This time cyanide is negatively charged, and the lone pair of electrons attacks the carbon, which is electron deficient, breaks the carbon-iodine bond, and we form our product. And that is nucleophilic substitution.